Good morning, sir. My name is Ujun Kai. My student ID is 0207157. And in this presentation, I'm going to illustrate about the industrial automation. So this is the agenda of the overall presentation. There are introduction, overview of sensor technologies, evolution of industrial automation, current trends, domain-specific relevance, characteristics and functional principle, main challenges and limitations, issues and broad impact, and lastly, conclusion. So we'll start with the introduction. So the industrial automation today is experiencing a major transformation driven by the Industry 4.0 movement, which is what we're in right now. So we are shifting from our traditional automated factories toward what is now called the smart factory. This transformation is made possible through the integration of cloud computing, the Internet of Things, also known as IoT, and cyber physical systems. So at the center of this evolution are sensor technologies. Sensors have progressed far beyond simple data collecting devices. They now act as intelligent network nodes that continuously communicate, process information, and support real-time decision making. So this advancement has also enabled the rise of the sensing as a service, or SaaS model, where sensor data can be accessed on demand without owning the physical equipment. So the industrial automation is a relevant and rapidly growing field with global market projections exceeding $200 billion by 2025. So because of its economic importance and its role in improving efficiency, this area was selected for analysis. So in this presentation, I'll be showing how sensors work, the key challenges they face, and the ethical and societal issues that arise, especially within the evolving SaaS landscape. Ultimately, the findings show that sensors are essential for achieving autonomous, resilient, and highly efficient manufacturing system. So we'll first take a look at the overview of sensor technology. So firstly, is the proximity sensor. So the proximity sensor could detect presence of an object without making physical contact. So for example, inductive sensors for detecting metal, capacitive sensors for detecting materials like plastic, liquids, and powder, and photoelectric sensors that rely on light beams, and finally, ultrasonic sensors that use sound wave. So these are common use in object detection, alignment, and safety application. So the second sensor I'll be talking about is the position sensor. It is used to measure distance, displacements, or rotations. It is an essential sensor for closed-loop control systems in robotics, CNC machines, and hydraulic systems. So the main examples or the main sensors are LVDTs that offer precise and contactless measurements, optical or magnetic encoders that provide either incremental or absolute position feedback, and magnetostrictive sensors, which is for high stroke, high precision applications, and lastly is laser sensors, which are extremely accurate calibration and measurements tasks. So the third sensors is the condition monitoring sensors. So there are vibration sensors, acoustic emission sensors, thermocouples, and RTDs, which are used to detect early signs of equipment failure, enabling predictive maintenance and reducing downtime. So the fourth type of sensor is the vision monitoring sensor. So they are high resolution cameras combined with machine learning and are widely used for automated quality inspections. So the example that I chose for this is the LiDAR system, which provide a 3D mapping and navigation for automated guided vehicles in warehouses and manufacturing facilities. And lastly is process variable sensors, which is used to as a pressure flow and level sensors, which are critical in industries like chemicals, oil and gas, and energy production. So the sensor is used to ensure the correct operating conditions and maintaining safety. So these are the examples of the sensors. So the proximity sensor, the one that I chose is inductive sensor. And in the middle is a position sensor, which is the magnetostrictive sensor. And the third one is a condition monitoring sensor, which is a accelerometer. So for vision and optical sensor, I chose LiDAR. This is the LiDAR sensor. And for process variable sensor, this is a piezoelectric sensor. So next, I'll be talking about the evolution of sensor technologies. In Industry 1.0 and 2.0, factories mainly use very basic devices like thermocouples and mechanical limit switches. These were simple on-off components with no intelligence directly wired into control panels. So during Industry 3.0, the introduction of programmable logic controllers, or PLCs, was a major turning point. So sensors became more standardized and could provide continuous feedback. So technologies like photoelectric and inductive sensors became common and allowed automated assembly lines to achieve higher reliability. So in Industry 4.0, sensors became smart network devices thanks to IoT, embedded microcontrollers, and miniaturized MEMS technology. Modern sensors can process data, communicate wirelessly, and even diagnose their own condition. And finally, Industry 5.0 is moving toward collaboration between humans and machines. So future sensors will have advanced AI capabilities, contextual awareness, and even biosensing features, enabling safer and more adaptive production environments. So next, I'll be talking about the current trends of the industrial automation. So there are several important trends define where sensor technologies are heading today. So the first is intelligent and diagnostic sensor. These sensors use AI or machine learning algorithms to detect anomalies, correct drift, and improve accuracy without manual calibration. So the sensor could detect for any kinds of error themselves and fix it themselves if it is not a physical error. So the secondly is wireless and energy harvesting sensor. So it could reduce wiring costs and can operate on harvested energy from vibration or heat, although energy output is still limited. So the third is edge cloud integration. Critical data is processed at the edge of speed, which long-term analytics happens in the cloud. This hybrid approach can reduce latency by up to 40%. And the fourth is cybersecurity integration. As sensors become more connected, they must include hardware encryption, secure boot, and even blockchain-based integrity checks. And lastly is interoperability and digital twins. Standards like OPC UA allow sensors from different manufacturers to communicate, and digital twins enable real-time virtual replicas of equipment and entire factory. So the next thing I'm going to talk about is domain-specific relevance. So these trends are not theoretically, they directly impact the industrial automation. So the first is the predictive maintenance. AI-enabled condition sensors can detect failures days in advance, reducing unplanned downtime by up to 30%, which is quite critical because you could save a lot of time and cost if you could prevent the system downtime. So secondly is precision manufacturing. High-resolution optical and laser sensors ensure micrometer level accuracy, which is crucial for industries like automotive and semiconductor production. So third is adaptive robotic. So the force, torque, and proximity sensors could make collaborative robots safer and more adaptive when working with humans. And lastly is the process industries. Multi-sensor fusion improves energy efficiency and optimizes resource consumption, with studies showing up to a 35% reduction in energy use. So next, I'll be talking about the characteristics and functional principle. So at the core of every sensor is a transduction mechanism, which is the physical principle that converts a real-world input into an electrical signal. So one of the most common mechanism is the piezoelectric effect, which is used in accelerometers and pressure sensors. When mechanical stress is applied to certain materials, they generate an electrical charge. This makes piezoelectric sensors ideal for detecting vibration, shock, or dynamic pressure changes. So another widely used principle is the strain gauge, where electrical resistance changes when a material is stretched or compressed. This is the basic for load cells and torque sensors. However, strain gauges are sensitive to temperature, so they often require Wheatstone bridge circuits for compensation. We also have electromagnetic induction, which is the operating principle of inductive proximity sensors. When a metallic object disrupts an oscillating electromagnetic field, the change can be detected. These sensors are extremely robust and commonly used in manufacturing lines. So for optical-based sensing, optoelectronic principles come into play. So for photoelectric sensors, they detect changes in a light beam, while advanced vision systems use CCD or CMOS cameras. These enable tasks like pattern recognition, quality inspection, and precise alignment. So this is the functional principle. So the first parameter is sensitive and range. For high sensitivity sensors can detect very small changes, but they may have a limited usable range. So choosing the right balance is very important. So the next is accuracy, which often involves a trade-off with cost. Higher precision sensors, such as laser interferometers, offer exceptional accuracy, but are much more expensive than ultrasonic sensors. And the resource time is another key factor, especially in high-speed automation. So for example, a photoelectric sensor on a bottling line must detect missing caps in a matter of milliseconds. So then there is linearity and hysteresis. Linearity refers to how closely the sensor's output matches the actual input across its range. Hysteresis refers to the small lag between increasing and decreasing measurements, which can cause persistent errors. These characteristics are critical in application requiring repeatable performances. In modern industrial sensors, often includes MEMS technology and integrated DSPs. This allows sensors to perform self-calibration, noise filtering, and even basic diagnostics before sending data to controllers. This reduces downtime, improves measurement accuracy, and lowers system complexity. So by overall, understanding these principles and performance characteristics is essential for selecting the right sensors for each application in industrial automation. And the next thing I'm going to talk about is the main challenges and limitations. Although sensor technologies have advanced significantly, there are still major challenges when deploying them in real industrial environments. So the first challenge is environmental resilience. Sensors often operate in extreme conditions like high temperatures, corrosive chemicals, high dust, vibration, or electromagnetic interference. So for example, in steel mills, normal contact thermocouples cannot withstand molten metal temperatures, so radiation pyrometers must be used instead. This shows how environmental factors limit the sensor choices and reliability. Another major issue is calibration drift. Over time, sensor readings gradually become inaccurate, even if the sensor is not visibly damaged. This drift can lead to poor product quality or unsafe conditions if not corrected. Newer approaches such as digital twins help address this by continuously comparing real sensor data with predicted values and identifying when recalibration is needed. So the third limitation is the power of and connectivity challenge, especially for wireless sensors. Technologies like energy harvesting can power small devices, but the power energy is unpredictable. This creates a trade-off between data frequency, transmission power, and battery life. So achieving continuous, reliable wireless sensing is still difficult. So another challenge is data fidelity and interoperability. Modern factories may use hundreds of sensors from different manufacturers, each with their own communication formats. Without standardization, data become difficult to integrate, creating what some call a data swamp. Standards like OPC UA help, but adoption is still inconsistent across the industry. So Cost is also a critical factor. The life cycle cost of sensor deployment includes installation, wiring, configuration, maintenance, and calibration. Scaling up to thousands of sensors for applications like full digital twins becomes financially demanding. This is why many companies are exploring cloud or subscription-based sensing as a service models, which is also known as SaaS models, to reduce upfront investment. So by overall, these challenges are interconnected. For example, if interoperability is poor, it affects data quality, which then impacts predictive maintenance. And if the sensor fail in harsh conditions, it increases the maintenance cost. So addressing these limitations requires combining better hardware, stronger cybersecurity, improved communication standards, and smarter analytics. And for the issue and broader impacts, besides technical challenges, the widespread use of sensors in industrial automation also brings several broader implications that affect cybersecurity, society, and the environment. The first major issue is cybersecurity and data sovereignty, because modern sensors are connected to networks and cloud platforms. They become potential entry points for cyber attacks. A well-known example that I found is Stuxnet, where compromised sensors played a role in manipulating industrial systems. With SAS, sensitive production data is often stored on third-party servers, raising concerns about who controls the data and how securely it is handled. To address this, industries are moving towards stronger encryption, secure hardware roots of trust, and even blockchain-based integrity checks. The second issue involves is the social economy and ethical impacts. Automation powered by sensor-driven systems can reduce the needs for low-skilled labor, which may lead to job displacement. At the same time, it creates demand for new roles in robotic maintenance, data analysis, and system integration. Ethically, continuous monitoring meant for machines can sometimes extend to monitoring human workers, potentially raising privacy concerns if not properly governed. Next, there is a growing concern about environmental sustainability. As factories adopt thousands of sensors, the overall volume of electronic waste increases. Many sensors contain metals, plastics, and components that are difficult to recycle. This highlights the need for more sustainable sensor design, such as using biodegradable materials, modular housing, and compliance with RoHS and WEEE standards. Another broader issue is systemic risk and resilience. Modern industrial systems rely heavily on cloud connectivity for analytics and monitoring. While this improves efficiency, it also creates a single point failure. If the network goes down, production may slow or stop entirely. This is why hybrid architectures that use edge computing are becoming critical, because they allow essential operations to continue even when the cloud is unavailable. So overall, these issues show that sensors are not just technical components. They have far-reaching implications that require cybersecurity measurements, ethical guidelines, environmental policies, and resilient system design to ensure safe and responsible use in industrial environments. So the last is conclusion. In summary, sensors are the backbone of modern industrial automation. They have evolved into intelligent, connected devices that enable real-time monitoring, smarter decision-making, and more efficient operations in Industry 4.0. Although challenges such as harsh environments, calibration drift, interoperability issues, and cybersecurity risks still exist, ongoing advances in AI, digital twins, and robust sensor designs are steadily overcoming these limitations. So looking forward, future sensors will become even more intelligent, self-powered, and easier to integrate, supporting safer, more autonomous, and more sustainable factories. Overall, sensors will continue to drive the next wave of innovation in industrial automation. And this is all of my presentation. Thank you.